All right, so now that we've defined what a power series is, let's look at an actual power series. So here's an example of a power series. So you get the sum as n goes from 1 to infinity of these powers of x minus 2 over n. So the constant that we're multiplying the powers of x minus 2 varies as n varies, right? So it's some function of n. So we want to know what values of x does this series converge. And we can find that by applying the ratio test. So let's apply the ratio test to this series to see when it converges. So let's look at the absolute value of the ratio of consecutive terms. So we get x minus 2 to the n plus 1 over n plus 1, right? That's the n plus 1th term. And then I'm going to multiply times the reciprocal of the nth term. So that becomes n over x minus 2 to the n. All right, so let's clean this up a little bit. So this is the same thing as x minus 2 times x minus 2 to the n, right? This numerator here on the left. And so I have a common factor of x minus 2. And so what I end up with, I'm leaving off my absolute value signs. So I'm going to have absolute value signs on in this case. So what I end up with is I have x minus 2, and then I have n over n plus 1. All right. So now we want to look at the limit as n goes to infinity of this thing, x minus 2 times n over n plus 1. Now, n over n plus 1 just goes to 1, right? And so what we end up with is just x minus 2, the absolute value of x minus 2, okay? And we know that this converges as long as that's less than 1, all right? So 1 is our radius of convergence. So this is actually called the radius of convergence. That's not always 1. It depends. We're looking for an interval around 2, because this is a power series that's centered around 2, right? That's our a value. So okay, radius of convergence. Oops, convergence. Okay. But we can actually take this a step farther. I can rearrange this a little bit, and so this actually means that x minus 2 is between -1 and +1, right? So if I add 2 to everything, I get x is between 3 and 1, okay? So now, but we're not quite there. So remember that the ratio test is inconclusive when when this x minus 2 is equal to 1, okay, when the limit is equal to 1. So we don't really have we're not really sure about these endpoints. So in order to get the interval of convergence, so this is kind of the start of an interval. We know it's everything between 1 and 3, x values between 1 and 3 will converge, but we need to test the endpoints. So so let's test those endpoints, because that's where it's equal to 1, right? Where this x minus 2, absolute value of x minus 2 is equal to 1. All right, so let's test at x equals 1. Okay, if we put that back into the original series, so we get n equals 1 to infinity, and if I put 1 in for x, I get 1 minus 2, so it becomes minus 1 to the n over n. And you should recognize this, right? You should recognize this is a series that we dealt with in the last section. It's an alternating series which converges by the alternating series test. Okay, so this one converges by the alternating series test. Okay, so we can actually include the point 1 in our interval of convergence. So let's look at the other endpoint, which is when x is equal to 3. So if we plug that into our series, n equals 1 to infinity, we get 3 minus 2, which is 1. 1 to the n is just 1, so we just get 1 over n. And that's our harmonic series, which we know diverges. Okay? So, so we can actually now state our interval of convergence as, let's see, right, interval of convergence. Okay, so now I know that it converges for 1, so I can say 1 less than or equal to x, but not for 3, so it does not include 3. Okay, or we could also write this as, so we include the endpoint 1, but we don't include 3. Okay, so that's another way to write the interval of convergence. All right, so I'll meet you for the next video.